Many of you know, many of you know about these psychometric charts, and in this psychometric chart, in the x-axis, we have got dry bulb temperature. In this curve, there is diagonal wet bulb temperature. These curves, these green curves are relative humidity, and the right-hand side, we have moisture, and sometimes we also have barometric pressure. So I'll just focus on the temperature on the x-axis, and you can see this is at base level, at the ground level, and this is at 600-meter height. So at the ground level, if we focus on summer, these green dots, they are scattered all around the places. So this temperature varies from 20 to 50 degrees Celsius at ground level. But if you look at 600 meters, the temperature varies almost between like 25 to 40. So the variation is lower, lessened, so it's more steady. So the higher up we go, it could be more steady. Okay, if we look at the next slide, now I'm going to show you some more real life data. This is very recent data, a couple of years ago. It's taken in one of the buildings in America. So you can see the temperature lapse rate in real life data. So you can see it's not a linear data as we saw in the lapse rate equation. It's reasonably non-linear. It's going down to some extent, then going up, then steady, and then again going down. So it very, very site specific. That's why monitoring is really important. In terms of humidity ratio, it doesn't change a lot. Now, temperature and humidity, they are not the only variables. There are other issues to deal with air quality. So if we look at CO2, if we go along the height, CO2 sometimes increases, sometimes decreases, again decreases and increases. So it keeps changing. It's very, very non-linear. Same to ozone and same to nitrous oxide. And more importantly, these days, in terms of indoor air quality, PM level is very important. So PM1, PM2.5, PM10, you can look at the definition later, but they're very important volatile organic compounds. So if we look at what happens to PM1, so we can see there is a change in PM1 level as we go along the height. Same for PM2.5 and PM10. So all these issues needed to be dealt with when we design a tall building. Another very important parameter is air velocity. So what happens to air velocity? Usually air velocity is in a very smooth site, in a countryside, for example, there is not much roughness in the terrain. This is an exponential curve with height. So if you go up, it goes up in an exponential fashion. And at some point, it reaches gradient height. What we mean gradient height is after gradient height, it becomes asymptotic, meaning that there is no change in velocity anymore, which is what we call gradient wind speed, and that is constant. And the plane where this velocity increase starts from, we call it zero plane. Now, the zero plane is the ground level when the surface terrain is very smooth in open countryside, for example. But in a suburb, to get that smooth surface, we have to go a little bit up these buildings. So that's what we call zero plane displacement. So the velocity exponential curve starts from the zero plane displacement. Same is true for urban centers. So there are so many tall buildings and medium-sized buildings. So the zero plane displacement starts a little bit higher up. So all this have effect on wind velocity. Now, we have to know that in a meteorological station, this air velocity is taken from an open countryside. So I'll explain it later further. Now, as you see, if there is a tall building, very tall building, the zero plane displacement will start from the average height of other buildings. And for this very tall building, there will be impact of the wind load as we go up. I mentioned of the meteorological stations. So this weather data, the conventional weather data that we use, usually taken from an open countryside, and the air velocity is taken from 10 meters height, okay? And relative humidity and temperature is taken from 2-meter heights. Now, it is only from 10 meters height, and this 10 meters, if you compare with this velocity exponential curve, this is only this height. So we get the velocity, this specific velocity that we get from our normal weather data. And we don't know about what is happening here, what is happening here, what is happening here. We have no idea. That's why we really need to know about this data. Now, the problem is conventional weather data are based on these measurements at 10-meter velocity, air velocity, and 2 meters temperature and relative humidity. That's our 2-dimensional conventional weather data. That's why we need 3-dimensional weather files. So there are some 3-dimensional weather files under development. One of them is weather research and forecasting 3D weather data. And this weather data looks like this. So we have not only x-axis and y-axis data for weather files, we also have weather data along the height with high resolution, maybe every 100 meters. So this kind of weather data can help us to design tall buildings in a better way. Now, this is an example with that WRF file of weather data. So this is a specific site in US. And you can see it in that site at 10-meter height. This is what we call a wind rose. So this wind rose shows what directions wind are coming and what velocity. So you can see in the 10-meter height, the wind rose, you can see predominant wind is coming from northwest and some coming from northeast. Now, if you go to 450-meter heights, there's lots of wind coming from north-south, so north-south, southwest. So that direction, if we use this weather file, we would not have known about this. That's why it's very important for tall buildings to know the weather variables along y-axis. Okay, so I'll wrap up with about this temperature and wind velocity with this nice curve, which shows that as we go up the floors, the temperature goes down and wind velocity increases. That is a challenge for tall buildings to deal with. Now there is an example of Jeddah Tower, which is going to be the tallest building in the world. And in this tower, the base at the ground level, the temperature is 30, for example, if the temperature is 30 degrees, and the top level, the temperature would be 25 degrees. There is a 5 degrees Celsius variation in temperature. What is the impact of it? One of the little example is heat loss calculation. So the very steady state heat loss calculation is Q equals U delta T. So this delta T is the temperature variation between indoor and outdoor. And for thermal comfort, if we want to keep our temperature, for example, 20 degrees Celsius inside, so the delta T would be 10 degrees Celsius here, and the delta T would be here like 4.5 degrees Celsius. So the delta T varies along the height, and that has an impact on our calculation of energy load. So sometimes we might undercalculate, sometimes we can overestimate, but this kind of data will help us to understand the energy use of the building in a better way. So this is an example of that calculation. I'll not explain all the graph, but let's look at this blue one. So this is, if we take the delta T as a constant, not regarding the height of the building, so that you can see the figure is here, 62. And if we take the variable delta T, the figure is 60, and there is lots of other numbers after that. So there is a huge implication of energy use. Okay, so that's my atmospheric part. Now I'll talk about passive design measures. So, and how to design a better building. So the way most of us know how to design a better building. Firstly, we have to reduce our energy load in the building using passive measures. And after using passive measures, we try to use the HVAC, heating, cooling, and ventilation system, optimize that so that we use the best HVAC system. Once we have the best HVAC system, now we try to meet that energy load using renewable energy. Okay, so that's the way to meet to a better building. Now, many of you know about the passive design measures, so I'll go just skip the slides very quickly. One of the key thing of passive design measure is to respect the site and respect the sun path. That is really, really important. So the building orientation will respect the sun path and the wind flow in the site. And another very key important variable is the shape of the building. Shape optimization is so important. I'll show it later. So you could have a round shape, you can have a square, you can have a circle, you can have so many different shapes, but which is the most optimized shape for that specific site needs to be done either by computer simulation or by hand. So I'll move forward. Another key thing is the heat capacity of the building. So what happens with heat capacity? Heat capacity is the capacity of the material to retain and release heat later. That helps to shift the peak load in cooling period. So it shifts the peak cooling load, and in the night time, we can use night ventilation to cool down the building to make it recharge in the daytime again. So that is one of the use of thermal mass. I will talk about it later again in our example building. The next one is thermal insulation. That's really, really important. That thermal insulation, what it does, it in building envelope is the first line of defense against climate. So these walls with high insulation value stops heat flux through the wall. There are very good standards these days about U values. One of them is passive house U value, which is about 0.15 watt per meter square Kelvin. which works quite well with buildings. Next issue is shading devices. So in Northern Hemisphere, where like in the UK, so the sun is inclined toward the south. So in the southern side, we have horizontal shading devices, and sun sets, rises in the east and sets down in the west. So in the east and west, they have a narrow angle. Horizontal devices do not work. We have to have vertical louvers. And that's very basic building physics. Everybody knows that. So I'll move to the next slide. This is daylighting. There are many ways of daylighting. I will skip this slide because we'll talk about daylight when we go to the example building. And next one is ventilation. Now, this ventilation is really important for tall buildings, and they behave completely different from the medium-sized buildings. In the medium-sized buildings, we can create natural ventilation with in an easier way. So using the buoyancy effect. So what is buoyancy effect? It is air moves from high density and high pressure to low density and low pressure. That is the nature of air. And high density and high pressure air is usually cool air. So cool air goes to the hot zone where there is a low pressure zone. So using that effect, I give you an example of a building. This is the BRE building near London. So they use this effect for natural ventilation, but to use this effect, we have to create buoyancy. That is the temperature differential. So they use these chimneys to create buoyancy effect. And then air moves from somewhere else and go warm up and go out this path, and that creates this air circle. Now, if we move to the tall buildings behave in a different way. Because of its huge height, they behave like a chimney. The whole tall building is a chimney. So in the summertime, the stack effect, what happens in the summertime? There is a cooler air outside, and we have a HVAC maintained warmer air, like 20 degrees Celsius inside. So this cooler air goes inside, take the temperature from the HVAC, becomes warmer and go out here, okay? And in the summertime, there is a reverse effect. So the warmer air goes here and take the HVAC cooled and become heavy, goes down. So it's cooler here, warmer there. So the pressure is outward. So air goes out. You can see it in the next design. So there is in the winter time, you have this loop that is creating the stack effect. In the summertime, you have other way around loop. So that is also a reverse effect. But you can see in my drawing that this is a thinner line, this is a thicker line, because in the winter time, we have higher delta T temperature difference, because winter time, we have internal temperature, for example, 23 degrees Celsius, outside temperature, let's say 0. So there is a 23 degrees Celsius temperature difference. But in the summertime, we have again internal temperature 23, but outer temperature maybe 30. So there is only 6 degree difference. So there's not much differential. That's why the effect is a little bit lessened. Now we move to the next slide. I just give an example of stack effect. So this red one is the summer stack effect. In terms of infiltration rate, I'm showing this graph. So there is, because of stack effect, there's much infiltration here, and this inflation goes up, and there is exfiltration. So air is going out. And some points in this y-axis, they are neutral planes. Usually there is one neutral plane, but you can see there are number 2 or 3 neutral planes, because you can see this little change here, because there is an open zone here from where air is coming from outside, and there is another zone here where it's going outside. So it doesn't need any more explanation. I mean, it's just to show you the graph. And in the summertime, in the green, you can see a reverse effect, but less attenuated, not as much as the winter effect. Okay, so we talked about stack effect and the pressure because of the stack effect. However, there is another important thing that we talked about before, that is this exponential curve of air velocity. So because of that, that has a huge impact on the building surface. As you can see, there is a turbulence in the bottom layer, there is the laminar flow in the middle, and there is another kind of flow on the top. And in the back side, you can see there is a negative pressure or almost neutral pressure there. That means that air pressure is variant in different surfaces of a tall building. And that would have effect on building stack effect behavior. I'll just give you one short example. So this is your air velocity. This is the stack effect. Now, when we add air velocity to stack effect, what happens? Let's look at the section along this line. So this is the section. So you can see there is negative pressure here, negative pressure here, negative. What we mean by negative pressure is air is going out, air is going out. But here you can see because of this air velocity, air is going in. That means building surfaces have different effects and have to be, these things have to be taken into account when we design a tall building. Right, so we talked about that the whole building works as a chimney. Now I'll show you a video to show what the impact of stack effect. Let's see if I can open the video. I'll open this one here. Yeah.
Hello, I'm District Chief Dave Woodrill with Denver Fire Department. I'm here with members of Engine Company 1 today. This is firefighter Ken English, and this is firefighter Jesse Weed. We're here at a 44-story commercial high-rise building in downtown Denver. And we just wanted to use a kind of a crude method to illustrate stack effect in this building. It's a very cold day today in Denver. It's about 10 degrees outside, and the ambient temperature inside here, inside the building, is about 70 degrees, making for a 60-degree temperature differential, which would contribute to a very powerful stack effect on this cold winter day. So I'll have firefighter Jesse Weed open the door, and firefighter Ken English is going to use this stick that we have streamers on to illustrate the powerful stack effect in this building today. So it's when you come into a building and you're using one of the standard doors on either side, typically of a revolving door, and you realize it's very difficult to open it up. That's just a positive stack effect, which is going to be very powerful on a cold winter day like it is here today.
So as you have seen, that stack effect has a huge implication on tall buildings. It's nothing to do with the small domestic nice ventilated building. It's a huge impact, and mostly it has negative impact on tall buildings. So some of the negative impacts I'm just have written it down here. One is the swing door operation. You just seen that the swing door was very difficult to open. And that's why revolving door is invented. Architects need to know it's not for design purpose, it's just functionally revolving door works better in a tall building to resist that pressure. Then elevator door operation, because elevator itself is a shaft, so stack air wants to go through the elevator shaft. So there is a huge pressure on the elevator door. Then the next problem is excessive air movement and propagation of smoke and odor throughout the building. Unwanted noise. There is so many different kind of noise created. If we have the stack effect problem, the building becomes very, very noisy with very peculiar noises. And the next one is increased rate of fire propagation. If there is a fire, it will spread so quickly with the effect of the stack effect. So what are the possible solutions? So some of the possible solutions, first one is to improve the air tightness. If the building is airtight, it is already pressurized, so stack effect would be lessened. Now, number two is revolving doors that we talked about already. Number three is vestibules in entrance and elevator banks. So by vestibule, we mean there's lobby space. So if we have a secondary space, that can work as a buffer for a stack effect. So that would be really, really helpful. Number four is vertical separation within stairwell and elevator shafts. So rather than having a long shaft going up until that height, if we break this height, that will break the stack effect as well. Horizontal compartmentalization helps. And another active measure is pressurization of elevator and a stairway shaft. And sometimes they also pressurize the base of ground floor so that can reduce the stack effect. But many building physicists suggest that it's better to pressurize the whole building in a lessened way rather than just pressurizing the ground level. And another very effective way is to divide a very tall building into small chunks of buildings, one after another, and just deal with them separately. Okay, so now I'll finish my passive measures with the last part is the very nice, envelope system, what we called double skin facade. So double skin facade, you can see in the double skin facade, we have a double or triple glazed window here, and then we have a single glaze. And in between, we have a space where we can have the louvers or blinds. So this, once we have it, we can control it in many ways. For example, this is summer. If we want natural ventilation, we can let air in. And so this air goes up and goes away again. So it doesn't become heated up. If in the summer, we want cold air, in the winter, if we want cold air to pass through, so the air can go through air and they become warm up and they just goes out inside the building. And there are other ways in the summer, if it is closed, we can run cold air through air and it becomes warmer and it goes out. So there are so many different ways we can use double skin facade. And double skin facade, the gap between this single glaze and this triple or double glaze could be different. Like it could be like 500 mil, or it could be like 2 meters, depending on how you design the building. Okay, so that's our passive measure. Now we'll go to HVAC systems. So I'll be very quick now. There are 3 types of HVAC systems: centralized system, partially centralized system, and local systems. I'll just go to the details. So let's talk about the centralized system. So there are one of the 2 key systems are constant volume system and variable air volume system. So basically, in these both systems, you have chillers and boilers and in a plant space, usually the plant space in the top of the roof or the second near the roof. So the chiller or boiler will heat up or cool down the air in the air handling unit. And this air will be sent to different floors and different compartments. Now, what is the difference between constant air and variable air volume? The constant air is air volume is always same everywhere. So you have same amount of heat pumped into all the places. You cannot change the temperature between different spaces. But in a variable air volume system, you have a volume control damper, which can be used to change the volume rate of heat flow. So we can pump different amount of heat to different places. Effectively, we have different temperature in different places, okay? The other centralized system is displacement ventilation. So the basic of displacement ventilation is heat or cold is flown from the floor level. So this is kind of the natural flow of air, because air flows from down to up as it warms up. So it needs less pressure and it slowly goes up and heated up and goes away with the extraction system. And in that way, it just serves its purpose, and it's a little bit less noisier because we don't have any fan anywhere here. Okay, so now we go to the partially centralized system. So the reason we say partially, because half of the system is on the top and half of the system in the building itself, in the floor. So one of the partially centralized system is fan coil system. So how it works, so in this case, we are not sending air or pumping air, we are pumping water. So we have chillers, we have boilers, but we are pumping either chilled water or hot water, depending on if we need heating or cooling. So this chilled or hot water goes here. And once it comes to the radiator, there is a fan which circulates this heat or cooled to the space, okay? So they circulate, meaning that they just keep circulating. We need another source of ventilation. So we need another air handling unit to manage the ventilation, okay? But it's a quick response system because of the fan and high temperature and high cool, because it could be quite low temperature. And that low temperature, Because of that low temperature, the moisture can condense here. And that condensate can be stored in the tray and later on drained. Now that means that it deals with both sensible load and latent load of heating or cooling. So that's efficient in that sense. Now, if we move to the next one, this is chill beam and chill ceiling. It's same like quite similar to fan coil system. So we have coils that can have chilled water inside, but in this case, this is in a beam that is under the ceiling. So you can do it in later on in a retrofit, and this could be whole ceiling could be a chilled ceiling. Now, what is the difference from fan coil? In chill ceiling or chill beam, the temperature is around like 10 degrees Celsius, so they don't condense water, so they don't work as a dehumidifier, meaning that they don't deal with latent load. So latent load has to be dealt with by a DUA system, that is a outside air system, direct outside air system. Okay, so that's the difference between fan coil and chill beam. So chill beam are reasonably slow response system compared to fan coil system. Now, partially centralized, the last one is heat pump. It's basically like our radiators. So you have all these radiators and you have heating system and cooling system. And the temperature is always maintained between 20 to 40 degrees Celsius, depending on what is required. Now let's go to the local systems. So the local systems are basically split air conditioner. So we have this wall mount split air conditioner, and we have an outdoor unit quite close to it. Now the problem with split air conditioner is like we have to have same. If we have heating, we have to have heating all places. If we have cooling, we have to have cooling in all other places. We cannot have heating and cooling together. To solve this, there is another system called variable refrigerant flow system, VRF. So in VRF, you can have heating in some places and cooling in some other places within these centralized local systems. Okay, so these are our HVAC systems. Now I just wrap up with what is the measures for sustainable design. So first point is we have to reduce energy load with passive measures. We try to reclaim heat from air and from water, whatever we use, we try to reclaim it. Then absorption. Absorption means we try to absorb the natural forces like wind, heating source or solar radiation. Then from there, we try to generate electricity. So that is the way forward. And in a building sense, it will be, we have a baseline building first. After that, we'll reduce the demand from the baseline building. Then we increase the efficiency of the HVAC system. Then we add renewable sources. Okay, but that's not the end. After the building is constructed, we have to have commissioning to test the systems to make sure the systems work. That's not the end as well. After that, after the residents starts living there or people start working there, we have to have post-occupancy evaluation after 6 months or 1 year, or if at intermittent times, to see how good the building is performing compared to the prediction. Okay, and that links to operation and maintenance. Now I will, before I go to my example building, I'll just define what is a net zero building. So the definition is very simple. The energy supplied to run the building and the energy produced by the renewables, either it will be same, equal, or the energy produced by the renewables should be more than the energy is required by the building. Now there's a little thing we have to focus on what we mean by energy. It's not site energy, it's source energy. So there is a variation between site and source energy. You can see here, if for electricity, 1 unit of site energy is like 2.8 unit of source energy. 1 unit of gas energy is like 1.05. This is in American terms. It depends on how the energy is produced. So it will be different in the UK. So I move towards now my case study. So I look at this building called Pertamina Energy Tower, which is a net zero energy building as designed. So it's a 99 floor building. and it's hotel and office. The client goal is to reduce water demand, zero storm discharge. And in terms of CO2 emission, the client requirement is to reduce by 26%. However, the SOM Wings and Merrills who designed the building, they wanted to also introduce solar, wind, and geothermal energy. So let's see how it goes. Before that, let's look at the Indonesian climate. So you can see the temperature varies between 23 to 32 degrees Celsius temperature. That means that we only need cooling, not heating. So it's a cooling dominant environment. So there is this tower, and it has other two buildings. One is a mosque and another is a pavilion. So how they dealt with all these buildings, we'll look at it now. Before that, water strategy. So they have a water strategy to use all the gray waters and black waters and filter all on site and reuse. As a result, there is a water demand reduction by 66%. There's net zero energy discharged outside and 95% reduction of drainage going out. So it's a very, very efficient building in terms of water use. Now we'll focus on energy use. So what are the passive measures taken in these buildings? So they took their influence from vernacular design of Indonesian buildings, and they tried to replicate these vernacular features in their shading devices. So you look at the shading device and here and there. So we look at each of the buildings and see what happens. So that's the pavilion I talked about. So you can see they try to replicate these vernacular elements to create shading. And you can see this is the perimeter zone of that building. This is the central zone of the building. And this building, as you see, the shading devices reduce direct solar radiation, and they have used VAV system, variable air flow system, in the perimeter because it's a quick response system. That's why it's used in the perimeter, and in the central, they use displacement ventilation. And the result is, compared to the ASHRAE baseline, the result is 39% reduction in energy demand. Now let's look at the mosque. So mosque is, you can see it's designed in different layers of envelopes here. And because of this envelope system, it has a huge thermal protection. However, they wanted to make the building naturally ventilated. So they try to use this buoyancy effect to naturally ventilate. And they see what happens if it is a free running building. So this is the CFD simulation, and you can see the temperature distribution in the free running building. And sometimes the temperature is 32, but in many cases it's like 25 to 27. And according to SOM, in Indonesia, thermal comfort is still attained if even the temperature is 32. One of the features of this building is, this mosque is particularly to use the thermal mass. So how they use this thermal mass? What they have done, they have got folded stones inside. So these folded stone panels, meaning that once you fold it, they have got more surface area. So they can absorb more heat in the daytime. And in the night cooling, they have night cooling system. So this heat could be released out. So they are ready in the next morning to absorb more heat. Okay, so in the mosque, also, I said that about the daylighting, there are so many passive measures for daylighting. So one of the measures is to use light shelves. So they use these light shelves. So the solar radiation light comes here and reflected from the light shelves to the ceiling and reflected back. So you have got diffuse light. So that's how they use natural lighting in this building. In addition to that, so we move to the next one. They also use LED lights. So the mosque energy balance, from the baseline, there is a 30% reduction in mosque energy use. Now let's move to the tower, what I've done to the tower. So that's very interesting. I said that shape optimization, and you can see that how it is. So you have a baseline, we have a baseline shape, and they tried to optimize it. First, they made it diamond shape, then rounded shape. And final shape, they have 49% reduction of peak cooling, just changing the shape of the building. And 30% annual demand is reducing, only changing the shape of the building. That's enormous. And now they did other optimization. They optimized just shading devices. So they used computer simulation tool to optimize, and they designed 675 profiles of shading devices. And in the optimization tool, they give 5 conditions, 5 parameters. And based on that parametric similar optimization, they found out their final design. And that result in trade-off between daylighting and solar radiation. And that is the final shading devices. As you can see in this picture, in the night, for supplementary light, they have used LED. As we know, LED is so far most efficient lighting systems. Now, what about the HVAC? So one thing I have never clearly talked about is what is the HVAC strategy in tall buildings. So usually you can see this perimeter zone and the central zone. So the perimeter zone is near the outside climate, and outside climate fluctuates rapidly. So the perimeter zone fluctuates also rapidly. So to deal with that fluctuation, we need a fast response system that can quickly respond to heating and cooling. So what they have used is fan coil system in the perimeter, and the core is reasonably steady state. So it's okay to use a chilled beam, which is a reasonably slow response system. And on top of that, because they have used a chilled beam, there is a need for separate ventilation system, which I said direct outdoor air system they have used. So DWAS system deals with the air and also with latent load. So on top of that, there is a heat recovery system. This heat recovery system is called double enthalpy wheel. The reason it's called double enthalpy because heat is recovered from the air and heat is also recovered from the moisture. So that's why it's double enthalpy. And that resulted into 48% reduction of the load from the baseline. So now in this tower, using all these measures, the reduction of energy demand from the ASHRAE baseline is 34%. Now let's add them together. So what happens is like overall there is a 30% reduction of energy demand in number. So what is the energy demand? Now the energy demand is 123 kilowatt hour per meter square per year, which is quite close to a passive house energy demand. In a passive house, the energy demand is 120 kilowatt hour per meter square per year. Now, the aim is to meet this demand using balancing demand using renewable energy supply. So the renewable energy supply they looked at is wind power, photovoltaic, and geothermal turbine. Let's talk about the wind first. So basically, they had to take the measurement of the wind at the crown of the building. So either monitoring or by simulation tools, that needs a 3D file. So based on that, they did their CFD simulation and they designed their wind turbine. So that's their wind turbine with vertical axis wind turbine. So they have got a number of vertical axis wind turbines. Now, next one is PV. They try to use PV or photovoltaic almost everywhere, including this path. You can see this path. On top of that path, they try to use PV and all these roofs. And that's the PV use layout. I'm just skipping that. I'm skipping this as well, just to mention that they use monocrystalline photovoltaic panels that has the highest efficiency. Now, talking about the geothermal, there are 2 types of geothermal. Normally, what we use is ground source heat pump. So the ground source heat pump just goes up until there. So it's a very narrow in terms of this geothermal we are talking about now. Now the geothermal that is used here goes 2 miles down where there is a hot aquifer with 200 degrees Celsius temperature. So they take this 200 degrees Celsius temperature water up to the top. And this is the water up to the top. It comes here, comes to a heat exchanger. And this exchanger then moves to another loop, which is by isobutane. And this isobutane loop runs an organic vapor turbine. And the organic vapor turbine creates electricity. Once you create electricity, it could be used for any purpose. So that's the geothermal. And I just move quickly because of time. So that is the organic vapor turbine. That is the heat exchanger. That they don't have much footprint, as you can see, quite small. Now, after all this, wind power creates 134 megawatt of energy per year, megawatt hour, photovoltaic 340 megawatt hour, and geothermal creates 40,000 megawatt hour. And if you look at the heat balance now, so total energy requirement is 38,417 megawatt hour. Total energy created is 40,740. That means 106% energy is created. That means it's a net energy positive building. Okay, so that's the end of my slide. So what I haven't talked about in this slide is embodied energy. We know that there is two aspects of carbon emissions. One is embodied energy, another is operational energy. Embodied energy has 30% impact on building's life cycle. So that has to be taken into account. We haven't talked about circular economy, reusing materials. So material side is not focused on in this discussion. Thank you.
Okay, thank you very much, Eshrar. That was really very interesting. We've had a couple of questions come in. So if you've got a couple of minutes, we'll take a few questions.
Yep, sure.
Firstly, can you talk a little bit about the sort of well-being, the effect of well-being of tall buildings, and also kind of things like occupants in a post-COVID world, kind of talking about sort of large mega buildings and things like the service cost charge of mega buildings compared with kind of more sort of normal sized buildings. Can you comment on some of those things?
Okay, firstly, in terms of well-being, it depends really. Of course, as there are impacts of tall buildings in terms of sometimes they find that people feel isolated in tall buildings. But then again, if we look forward to bioclimatic tall buildings with lots of spaces for interaction with greens that have separate investors, this is so subjective and these are so recent. The more research is needed to see what is the impact. People living in tall buildings, and there is not really very bad impact we have seen for living in tall buildings, that not people are always jumping from the top building. So it's very difficult. But there is a common idea that tall building people might feel isolated, but there are other options like using more greens, more communal spaces, and you can have lots of tall buildings linked together. So that's subject to research, I can say. Yeah. So what was the other question? Is the energy cost? It seems that at to some extent, to some height, it is still energy cost efficient, because we have to take into account also the land cost. And land cost is very high. Normally we do tall buildings in places where land is very high density places. And in those places it makes sense, but in terms of cost, it doesn't make sense to make a tall building in a place where you can easily build, you have got enough space available and you can easily build small buildings. Okay. I think, yeah.
Okay, thank you very much. We're running a bit of tight for time, but just one more question, if that's okay, Eshrar. Yeah. So somebody said, what's the benefits and disbenefits of buildings being completely off-grid, so being self-contained, particularly with regard to sort of energy use?
Okay, so there is a word now getting momentum. It's called thermal autonomy. Thermal autonomy means that if suddenly you lose all the electric connection, all the electric supply, is your building going to be survive in that situation? So for thermal autonomy, this is very important, the building to be able to work to some extent standalone. So it's very important, because off-grid is you don't depend on the main supply. And for one of the example is that somebody said once that if New York is cut off from the other cities, although in a different context, there will be no food supply to New York. And after 7 days, the whole city will collapse if you just close the city from other supplies. So because they don't have their own generation. So to have your own generation, say it electricity, say it food, it's really important.
Okay, thank you so much. That's been really interesting session. I hope everybody's enjoyed it, and thank you very much for attending today. I'm afraid we're going to have to kind of close things there just because of time, but thank you for all your other questions, and we'll try and answer those after the session as well if we haven't managed to cover those during today. Thank you very much. We're going to sign off now. Bye-bye.
Thank you. Thanks. Cheers. Bye.